All right, cool. Let's do that. Okay. All right. Hello, everybody. My name is Angie. I'm the lead of community team for Aiven, which probably none of you ever heard of. Has anybody here heard of Aiven before? Yes. 2 people. Excellent. I think half of them work for us. That's great. So these are not Aiven meetups. These are open source data infrastructure meetups. We hold them for the community. We provide pizza. We provide amazing speakers. And you come and you learn stuff, and we all win. But I will do a little bit about Aiven. Aiven is the open source data platform for everyone. So we run a whole bunch of your favorite open source technologies on one integrated data platform, and you can use it on any cloud that you want. That's enough about us. If you're here, we abide by a code of conduct, which means please, be kind, be respectful to one another. If you see anything that doesn't fit with that mold, please come talk to me. If you don't want to talk to me because I'm scary, you can email this email address and someone from our community team will reach out to you. But hopefully that's not an issue. We got pizza, we got pop, we're all in a good mood here. So I want to talk about our agenda. We have three great speakers tonight. We have Maurice from Hookdeck, who's going to be talking about scaling analytics with Clickhouse, with a whole bunch of interesting statistics behind that. So I'm really looking forward to that. We also have Dipankar talking about Apache Iceberg, which is a really cool kind of large-scale analytics technology. And then finally, we'll have Ankit joining us later from Instacart. He's going to be talking about how at Instacart they use Postgres as a search and personalization engine. And yeah, me too. Actually, I would love to know how they do that. And anyway, and then we'll end the evening with more of what we were just doing, just kind of talking, networking, that kind of thing. So yeah, welcome. I'm going to go ahead and pass it over to our first speaker. So Maurice.
Thank you.
There you go.
Thank you, Angie.
Yeah.
All right, let me get set up here. I think you need to stop sharing.
Oh, I do.
It's on, isn't it? This?
Hit it one more time because it's blinking, which means it's on. There you go. You're good.
You guys don't want to see my calendar, do you?
It looks busy.
That's not what you came for.
Here, I can use that for a second.
Yeah. Just let me.
While setup is happening, can I just hold? How about a show of hands? How many people here would call themselves software developers? Okay, roughly a third of the room, maybe half of the room. How many people here would consider themselves data engineers? Okay, right on. How about platform engineers? Do we have any of those folks in the house? I am so sorry. That is a job, isn't it? Yeah. That's a whole situation. What else we got? Shout them out. Who else are you here? What are you doing here? What are you hoping to learn? Data analysts, right on. Other data analysts, anyone? Cool, a couple of you. The reason I'm doing this awkward exercise, by the way, is because there's networking after, and it's really annoying when you're like standing against the wall and you don't know who to talk to. So it's like trying to give you people to talk to. Anyway, that was a nice segue too. Here you go.
Thank you very much. Good evening, everyone. I am Maurice. I'm CTO and co-founder at Hookdeck, and I'm going to talk to you tonight about why we chose Clickhouse plus Aiven for our user-facing analytics on Hookdeck. So first, before we dive into things, oh, that's not good. Why is that cut?
Oh.
I do have a fallback if this doesn't work, so bear with me one moment, but I'm good. We're going to try to make it work, but if it doesn't work, I do have a technical difficulties here. It doesn't like the aspect ratio. All right. Okay. Never mind that. Take two.
Take two.
This is why I saved it as a PDF.
Oh, always prepared. Look at that.
There we go. Okay. Now all I have to do is figure out how to maximize this. There we go. All right. Okay, so what is Hookdeck? Hookdeck is an event gateway, and what that means is, so Hookdeck actually started as a webhooks processing platform. Show of hands, who here is familiar with webhooks? Cool. So webhooks is the mechanism that a lot of platforms have decided to use to communicate asynchronous information, real-time information. So traditional world, we've had APIs. We need to get some information from certain system. We pull from an API. And if you need to get that information at the semi-real-time data, you keep pulling the API, and then ultimately you hit the rate limit, and that platform blocks you, and then you're very sad, and you can't get your data. So the response to that mechanism were webhooks. Webhooks are basically the principle of the platform saying, don't call us, we'll call you, right? So we'll send you an event whenever something interesting that you're interested in happens on the platform. You have to subscribe to the event, and we'll send you that event. Now, if you kind of look at the SaaS market as a whole in the past few years, one trend that we're starting to see, or that I think we're starting to see, is a hyper-specialization of SaaS platforms, which means that they operate in the verticals that they're really good at. Take Shopify, for instance. You know, Shopify used to do a wide variety of things, but now there's fulfillment specialists, there's messaging specialists and stuff like that that integrate all with those platforms. You know, Shopify being one of the most notable examples. A lot of customers that use Hookdeck are on Shopify, and the amount of webhooks that they can send for reasonably large applications. So we have one customer, for instance, that runs a very successful customer service application on Shopify. He has about, I think, 200-300 customers. Take a guess at the amount of webhooks that these guys process in a month. Wild guess. Any number.
10 million.
10 million. Anything else?
100 million.
Other guesses? It's more.
500.
More.
1 billion.
3 billion.
Whoa.
So if you do and you break down the math, I think that works out to a few thousand per second. So the point is that the volume of webhooks has increased a lot recently, and that just managing them, you have to build infrastructure to manage them, you have to build queuing systems, etc. So this is what Hookdeck does. This is what we built Hookdeck for initially. But as we kind of went through this journey, we started seeing a bigger opportunity for Hookdeck, and the opportunity was actually just processing all kinds of events, not only webhooks. So webhooks are HTTP, webhook use, an HTTP transport, webhooks use certain characteristics, and, we started seeing that we could do that for other transport layers as well, other formats, and that's why we're talking about, we're starting to talk about an API gateway. So an event gateway, I'm sorry. So how does an event gateway compare to an API gateway if you're familiar with the concept of API gateway? I'm not going to go too much in detail around that, but basically think of things like rate limiting. When you rate limit for an API, right, you're stopping the caller or the client from hitting your API when they hit a certain rate that you set, let's say 5 per second, right? In the event world, what you're doing is that you're throttling the delivery on the event gateway side. So basically you're accepting all the events, but your throttling is happening on the processing. So you say, okay, I'm going to take it in, but if you're over your rate limit, I'm going to slow down the processing so that I can catch up, but I'm still going to accept your event up, obviously to a certain acceptable rate. But that's kind of the idea. So durability, when you receive an event, we basically persist that event on the platform so that you can replay it, you can retry it, you can pause it. And by the way, I'm giving you all this information because that kind of goes into what we're going to talk about and why Clickhouse came into the mix. So it's all going to tie together. So that's a little bit about Hookdeck as a whole. So as we started growing and as we started onboarding more and more customers, we made a very early technological choice to go with Postgres. Why Postgres? It's easy, it's accessible, lots of libraries. We wanted to prototype, we wanted something that was fast to put to market. So we went with Postgres. We're processing a few million events a month. Life was beautiful. And then from 1 million, we grew eventually to 10 million, to 50 million, to 100 million, to a few hundred millions at the point that we are today. And Postgres works great when you have a few million rows per table, works great when you have a few 100 million rows per table, but your queries are going to slow down, right? It still works actually really well. We still have Postgres in production, but our Postgres right now is processing about 10,000 commits a second, so 10,000 transactions per second, which is a lot of volume. I mean, for us anyways, right? I mean, I know other companies with bigger clusters have probably scaled Postgres beyond that, but for us, it's pretty big volume, and there's cost concerns there. And when I say cost concerns, it's not that it's overall absolutely, as an absolute, it's expensive. It's that for the price that we're selling our product for, it just doesn't make economical sense, and the economies of scale don't work anymore. So we had to look for another solution, at least to solve the problem of data growth, right? The big thing was, like I said, query performance. So what you see here is our dashboard, and there's, one of the pieces of information that we have on our dashboard is a histogram of what's going on over time. So your event delivery over time. We have also a list of events, and we have a bunch of filters on top that you see there in blue. And the big problem we were running in is that we were spending 30 seconds to minutes to load all that data on bigger workspaces. So on our customers that were actually sending a decent
All right. All right. Hi, everyone. Thank you so much for joining us today in this Toronto Open Data Infrastructure Group. I'm going to talk a bit about data architectures, and I'm hoping at least like a couple of them, because I saw a couple of raised hands. So I'm hoping that a couple of you are at least aware of like the evolution of data architectures, how we move from like data warehouses to like data lakes, and more specifically, I'm going to talk about like a lakehouse architecture and how Apache Iceberg as a technology enables that. So a little bit about me. My name is Dipankar, and I'm currently a data engineering advocate here at Dremio. I focus on open source projects like Apache Iceberg, Apache Arrow, Project Nessie as well, and my focus really is on the data architecture part of it and platform of it. So my talk is pretty much going to be around that, and I'm going to like basically demystify like the term of lakehouse and technologically enable how that works. So I'm also currently co-authoring the first book on Apache Iceberg. It's a O'Reilly book. So basically, it help people like data architects, data engineers to develop and build platforms using Iceberg. So that's what I'm working on. Again, this time is very limited, so I'm sorry that I'm not going into that level of deep here. But hopefully you can catch with me like after the session or even on my LinkedIn on socials. I'm pretty active. Yeah, right. So yeah, hopefully you can catch with me after the session or even on my socials. Feel free to like shoot me a message and I'll be sure to reply there. So in terms of the key takeaways today, I mean, I'll start with a kind of a basic evolution of data architecture, how we have evolved throughout the industry. I started my journey with like data warehouses, data lakes, into various roles like BI and ML. And then we will come to our focal point, which is our data lakehouse. What exactly is a data lakehouse architecture and how Iceberg as a technology enables that. And finally, we'll also go through a production use case. Basically, Iceberg started at Netflix. So Netflix's engineering team co-created Iceberg, and then they made it open source. And they basically incepted from the idea from that the Hive table format was widely used in Netflix all over, like personalization and recommendations. And it had some shortfalls that we are going to see today. And those shortfalls helped basically in the development of modern table formats like Apache Iceberg. But also just to give an idea, there are two other table formats that are also used in the industry today, which is Apache Hudi and Delta Lake by Databricks. So these are the kind of three table formats that you see today. So the whole idea was that over the years, organizations have been heavily investing on building kind of centralized and reliable data platform. The idea was that if they could democratize data, they could also enable like data consumers. So for me, data consumers, I like being a data engineer. For me, data consumers are basically data analysts or data engineers who are trying to basically use that data and do all sort of analytical workloads, whether it's BI, whether it's ML, streaming, whatever it is. So the idea was that if they could build a centralized and reliable data platform, that would enable democratization of data, and that's how we have come like in that process throughout that. So data warehouses were kind of the first one that enabled that, and to me, data warehouse is just more of a analytical database, OLAP database. So that was the kind of first one that enabled that kind of thing. So you could store any kind of structured data on a data warehouse for analytical purposes. And then once you are ready with kind of transformation and stuff, you can basically use it for your reporting and other sort of workloads. So then came the era of Hadoop and elephant in the big data world. So data, that's when like the idea of a data lake started. So Hadoop was the kind of the first on-premise data lake, if you may, that basically had a kind of file system, Hadoop file system. It enabled you to basically dump any kind of data, whether it's structured, unstructured. The problem with the data warehouses were like we were limited to only kind of relational workloads. I mean, today we have like cloud data warehouses now, like with Snowflake or BigQuery, where you can also do things like ML and unstructured data. But at least at that point of time, it was really a hard time to like, for specifically for like data scientist kind of persona, where they were trying to like, get some data from a data warehouse, export the data, had to kind of like wait for like long wait requests and stuff. I myself was in that position for a long period of time. And then we had this kind of data lakes where we were able to, okay, at least we were able to like get some kind of unstructured workloads. And based on that, I could, build my models and stuff around that. So that was primarily data lakes. But data lake obviously had some issues, obviously, and that's why we have something like Lakehouse today. So one was that you just can't dump all of your data in like a, like a file system like that, right? You need to be able to like, you can't just let your analyst or scientist, deal with the kind of physical bits and bytes and the files of the data when you're dealing with it. Also, like for kind of BI and relational workloads, you typically what you do, industries, how they work is basically they export the data, like I said, and then you would put it into a data lake, and from there you go on from there. But the most important problem in a data lake was that it kind of lacked those transactional guarantees. So, for example, imagine two different engine, let's say Spark and Trino. They are trying to write the data, in a particular file system. At the same time, those transactional guarantees were kind of missing in the file system. And because you didn't have those kind of database-related ACID properties, there was no consistency in those transactions. So things like concurrent writes had no guarantees, and that could lead to consistency issues in the tables, which ultimately will impact the downstream analytical applications. So that was kind of like the main idea behind having something like a lakehouse architecture. Also, to add to that, it was really hard to make sense of any kind of data from a object store or a data lake file system, because there is no real governance, there is no data quality checks. Even if there are quality checks, it's at a very a team level hierarchy. So I think that was kind of the main problem with this kind of data lakes, and that basically led to the data lakehouse architecture. And as you can probably guess from the name, lakehouse, it's a combination of a data warehouse and a data lake in some capacity. So how I try to put it is that it kind of takes the best of a data warehouse and best of a data lake and tries to bring everything together. So now you can basically run any kind of workload that you used to run on a data warehouse with all those kind of transactional guarantees on a database or any kind of OLAP database, but still have the kind of scalability and agility of a data lake. So modern data lakes primarily are kind of hosted by the three major vendors of cloud, whether it's AWS, Google Cloud Storage, or GCS or Azure Blobs. So these are kind of the new modern data lakes object store that enables you to really scale your storage, and the cost factor is also a very important aspect of this, because all these things look good at a smaller scale, but when when you're dealing with a larger amount of data, it kind of is hard to deal with kind of cost factors and scaling. So that's what basically led to kind of merging these kind of two different kind of architectures, taking the best of those things. For example, with a data warehouse, you can do things like schema evolution. You can basically change the schema of a table. You can do time travel and go back and do some past analysis. Also things like compaction. So all those things are happening in the background, and data warehouses used to provide that in a very native way. Whereas in a data lake, you didn't have that, but you have all these benefits in terms of the cost and scalability of the storage. So just to give a visual picture, I'm a person, I was a data visualization engineer in the past, so I like to see things visually, and also it kind of leaves a mental impression. This is one of the things that might be among all the things that might be one of the things that you might want to take away from my presentation. So this is the architecture in general of a lake house, and I just want to make sure you understand how Iceberg and where Iceberg fits in this particular architecture. So I'll start from the bottom to the top. That's how it usually works. We usually call it downstream analytical applications, but it's either other way around. So the first part, obviously, and then I'm going to draw a comparison between a data warehouse or a database, just to have that kind of understanding. So we start with the storage first. Obviously, the first thing is that you need to store your data. And in this case, we have the data lakes. So whether it's S3 bucket, whether it's ADLS or GCS bucket, or something like on-premise a file system like Hadoop, you can basically land all your ingested data in this particular storage systems. And on top of that, you have the file format. That's another component of a lakehouse. So the file format is actually where the data is written, right? That's where the data is originally stored, all the bytes. So at least in the last past 10 years with formats, in the past 5 years with formats like Parquet or these are columnar file formats. So they provide some additional benefits in terms of for example, predicate pushdowns, ability to rely on things like statistical information. So you get to know about things like, okay, you have a file, you can get information about the minimum and the maximum value of a particular column, or the null value counts and those kind of things. So those has been in use recently, at least in major organizations like Uber, Netflix, and stuff. But also, you're not just relying on that. Iceberg supports all the other formats like CSV, JSON, whatever it is. And on top of the file format, that's where comes our table formats, which is basically Iceberg or Delta Lake or Hoodie, whatever it is. In this case, I'm going to talk about Iceberg. But basically, what Iceberg is doing here, it is just an abstraction on top of those file formats. So ultimately, what we're trying to achieve here is that you have these raw data files like Parquet or Org that are landing in the data lake storage like S3 bucket. But for an engine to be able to query them, you need to be able to have some kind of a schema, and be able to refer to that kind of data set with a schema. Otherwise, for engines, it's really tough. Like for Spark or any kind of engine, it's really tough to understand and do immutable operations on those files directly. So that's where Apache Iceberg comes, and Apache Iceberg brings like things like schema evolution, SQL semantics. You can easily use SQL. You don't have to really learn a new thing or something. And really, the whole idea here is that if you notice each and every block here, they're separate blocks. They're not tied up to one bundle unit. So if I have to compare like with a data warehouse, like for example like Snowflake or BigQuery, pretty much all the components are also present in that kind of storage, in that kind of environment. It's just that they're bundled up into one single thing. So basically the file format and the table format that you see here, it's very proprietary to their own system. So that means your compute engine is only able to access data that is in their particular format, to Snowflake's format or BigQuery's format, whatever it is. But in this case, since data is kind of in an independent tier with like open file and open table format, you can really bring any kind of compute engine that you want for your particular use case. So for example, if you're doing like distributed ETL and stuff, probably Spark would be like your thing. Or if you're like running like BI with like data lakes, my company, I work for Dremio. We build the compute engines as well. So that's where Dremio comes in for ad hoc SQL kind of analysis, BI, and kind of materialized views on top of data lakes and those kind of things. Also, if you're dealing with streaming, like you can bring like something like Flink. Flink also has support for that. We also there are other bunch of compute engines as well. And then you have the the users and the application that are basically whether it's a Tableau dashboard, whether it's Superset, a PyTorch library or a scikit-learn library, using data directly from Apache Iceberg as a data set. So in that case, you are just relying on, you're not relying on exports and this kind of tedious process of ETL and directly accessing the data in this case. So that's pretty much about the Iceberg and how it sits in a kind of a lakehouse architecture. And hopefully that has presented at least some level of idea in terms of at least like how kind of it's segregated it is. And basically you are allowed to like choose and bring up your own technology that you want. For example, if I'm going to build a lakehouse, I can just use a S3 bucket, have some kind of file format, Apache Iceberg as a table on top of that, and use Spark as a compute engine on that. So I've been talking about table format without really going on what is a table format, and I think it might be a good idea to just to get an idea. This is not a new concept at all. Like so, usually with databases, we have seen the concept of tables. Of course, companies like Oracle, Microsoft, they have worked on it like a couple of years now with relational databases. So basically, it's a way to organize a datasets file in the form of a table. So users don't really have to know about the kind of the physical bytes and the files, and they can just have that abstraction on top of that. So that abstraction is basically what is giving you the kind of the table format. Now in the big data world with Hadoop and HDFS, we ended up ultimately with like Hive. So most people can have access to the data because there was a need really like to if you are from that kind of Hadoop era, like you would understand like there was a need for like analysts, like they couldn't really access the data that was sitting in a data lake without really having the kind of abstraction on top of that. So that's when like Facebook like bought something like a Hive table format, and that allowed you to like have that abstraction. So now you query that kind of data with something like Hive query language, which is pretty much similar to SQL. So that was the kind of the old way of doing thing. So with Hive, what was there is that a table is basically a collection of directories, and all the directories will have the kind of the files that I was talking about, whether it's CSV, Parquet, Avro, whatever it is. But ultimately, those directories, they make up a table. So that was the concept of a table format in the world of the Hive. And let's talk about it in some more detail. So like I said, a table content is all file in a tables directory for Hive. Here, obviously, we can see like a couple of them, but obviously at scale, this would be like a lot of directories. And the tracking is done at the folder level, right? So the tracking of the folders is done at that level. And kind of this has been the standard, like, all throughout the years, like, they have been the de facto standard for a lot of organization. When like Facebook brought it, like with SQL, no map reduce job, you didn't have to write a big algorithm to like, process your data, reduce the data. And, basically it was enabled kind of a democratization of data, if you may. And that allowed more people, like I said, to use kind of your data that was sitting on a data lake. So definitely being that de facto has some advantages, and of course, like, we are going to talk about the disadvantages, because that's how we are going to end up with Iceberg and like all the other modern table formats. So I'm going to be quick. I'm going to just walk through a couple of the pros and cons. First was like Hive worked with basically every engine, right? Whether it's Spark, Trino, whatever it was, it could work. At least up until that point, there was no such table format that enabled multiple engines to work on the same data set at the same time. Next, it's kind of file format agnostic. So whether it's Parquet or CSV, it didn't matter. You could use any kind of file. And then you could also atomically update a whole partition. So what I mean to say is that, so for example, if you take a whole partition, you can change, you can write some data into that particular partition at the same time, but you didn't have, when you're writing it, no one sees those changes. So basically that thing is abstracted. And when you're done writing the data, basically you swap that reference of the metadata pointer in a meta store. And that's how we came with the idea of a Hive meta store, which is also really famous now, at least used in as a catalog in major companies as well. So this is how kind of Hive achieved those kind of atomicity and consistency guarantees and solve this problem with data lakes. And most importantly, it was kind of like a single central answer, right? You could just go to one particular centralized Hive table and just say, hey, what data is in my table? And can I query it using SQL? At least SQL semantics, and you could just get back the data. In terms of the cons, one of the things that we noticed was that the smaller updates were kind of very inefficient. So for example, because you only atomically update a whole partition, if you only want to change a few rows and a lot of time, it's going to be really inefficient and costly. So that is one important con. And you had no way to change data in multiple partitions safely. So what I mean to say is that although I mentioned that you could atomically update a whole partition, there were some level of guarantees that was not there when you were doing changes in the multiple partition at the same time. And specifically when you had multiple jobs doing it, multiple engines coming and writing data at the same time, it kind of was to be honest, in my experience, mostly practically it worked most of the time, but sometimes there also would be a lot of failures, and we are losing those kind of consistency and guarantees in the tables. Ultimately, that impacted our downstream applications and the reports stuff. So that was kind of really a triggering point for even from my experience. Next, all the direct listing needed for last. So basically, although in a Hive table everything is a directory, for an engine like Spark or Trino or Presto, it basically has to go and open each and every directory, and then each and every file within the directory, open, read, close, and it happens for every single files and for every single directory. And that is a problem, because at a major scale, this could be taking a lot of times. So that was one of the main problems that we kind of saw in Hive. And then, users have to know the physical layout of the table. I'm not going to touch more about that. This is more about the partitioning aspects. So, for example, in Hive table format, when you wanted to do a partitioning of the table, you basically had to add and basically incorporate a new column. It was a new partition column. So in that case, if your table is partitioned by, let's say, date, and if someone is querying using date time, Hive wouldn't automatically know to convert that transformation. So basically, users have to know the exact kind of partition, scheme, and that is kind of a tedious task to educate and all those analysts and scientists. Again, Hive table statistics. They were table statistics. This table statistic information are super useful for things like partition pruning, skipping data files which are not relevant. So I think it's important that we kind of gather this information. But the problem with Hive was that you had to run a separate job every time to collect the statistics. In practice, it's kind of hard to do that. And when you're running a lot of workloads, it's really hard to do that. For a smaller team, that could work out in some level, but it's really hard at scale. So these problems are pretty much common in most of the organization at scale. And if we talk about the whole point of where Iceberg incepted, for Netflix, they were kind of the main one to look at this problem, because obviously they were dealing with kind of large data sets at scale at that point of time. So they went to the drawing board and they were thinking of it instead of putting a band-aid to kind of each and every solution, why don't we take kind of a step back and try to understand if there is a kind of much easier approach to do this. And they had some kind of goals, like every organization. To be honest, these goals are pretty much common in every organization. But I'm going to just go through Netflix's goal. This is directly from Ryan Blue's presentation. He was a big data lead at Netflix. He co-created Iceberg, and this is from his presentation slide. So one was the table correctness or consistency. I've been talking about it a lot because I cannot stress the impact of it in the downstream applications and how it impacts the decision making as a whole. So I think that's super important. No matter whatever queries you run from whatever engine, you always should get the same data from the same table. Next is around fast query planning and execution. So I'm going to talk about the use case, but one of the query they ran, it took 10 minutes just to plan the query, and just for a week of data for one metric. So they're not even running years of data, whatever it is. So users are not going to wait that long for execution of those queries. And they don't want users to worry about the physical layout of the table. Like I was saying, users don't have to know about that, kind of bytes and bits and the partitioning scheme. It's really like tough. Like, why can't we have the software take care of that part, right? Why not, like, dedicate it to the software? There were also a lot of problem with the table evolution, like, and this is something we see usually, right? Business requirement changes. Today I'm working on a particular table, and suddenly, I come up with like some new schema level changes, and it's mostly like you have to, like, with Hive, at least I had to like basically rewrite my entire tables as a last resort. Although, like, there are some intermediaries in between that you can use, like, for example, like, copying table. Again, copying is a very expensive operation at scale, so that's something we have to be careful about. And to accomplish all of this at scale, that's the major problem. Like, you can deal with all this problem maybe at a smaller scale, but when you're companies like Netflix, or Uber, like, it's really hard, So when looking at all these problems and, kind of intermediate solution, all they could understand and, try to analyze was that the problem was that, the solution was that if they could basically change the structure of it by removing the directory structure to just files. So basically, that's the only change that they did. So Hive was all designed with the concept of directories, and they realized that basically it was taking a lot of time for queries to run. So they basically changed everything to a file. So with Iceberg and all the major table formats now, everything is actually a set of files, and those set of files. And if you remember from my slide before with the visual, that's why I have the file format below the table format. So that means you have the abstraction on top of the files. So you can really mitigate all these cons that we discussed with this kind of small change, and this is where Iceberg came. But just to recap what Iceberg is and isn't, you might have a lot of questions like, is it like something like Spark, is it like a query engine or whatnot? Technically, it's a set of APIs and libraries that basically any kind of compute engine will use to interact with that file formats. It's a table format specification, and it's not a storage engine or execution engine or Spark or something like that. So it's basically a set of APIs. And that's why it's also very lightweight. Now, I don't know how much time I have, but like, yeah, I might just do like a quick dive of the architecture just to give an idea. So basically, this is what the Iceberg architecture look like. 3 layers are there: catalog layer, the metadata layer, and the data layer. The best part about this architecture is that the data and metadata, they reside in the same kind of data lake, the same system. So you're not relying on a Hive metastore for all those kind of guarantees and stuff. So the catalog layer is the first component. It's basically that is basically where you find the current metadata layer location. So for example, let's say you're running a query like select star from something, and what that query will do is go to the catalog and ask, hey, can you give me the latest metadata file? And based on that latest metadata file, it will basically traverse and go through that kind of directory structure from the metadata file to the manifest list to the manifest file, and finally get the data file that is required by the particular query. So that's how the architecture of like Iceberg is overall. In terms of what can be a catalog and what cannot be, technically a catalog can also be like a database or a data store. So you could use something like a Postgres or something like that. But again, there are other options, like if you're using something like AWS ecosystem, AWS Glue is a great option here as well. We have an open source product called Nessie as well that sits well as, and that gives you like things like a Git-like things for data. So you can basically create your kind of own local environments for data and without really impacting other environments and do those transactions. And that's basically what like the overall catalog looks like. So the next component is basically the metadata layer. So which is what our next topic is, which is a metadata file. So once you open the current metadata file and you know that, okay, this is my version of the metadata file, you can get information like snapshot and manifest list. So what snapshot is basically in the Iceberg world is any kind of operation that you do in a kind of Iceberg table, whether it's insert, update, delete, everything is recorded as a snapshot, and it's a state of a table at a certain point of time. So that snapshot information is then used to find the manifest list path, and finally from the manifest list, we go on to the manifest file, which actually has information on things like the statistical information that I was talking about for pruning those files and making sure that we don't really, because the whole idea of a big data system is to read as much less data as possible. And in order to do that, what we want to do is we want to skip as much files as possible that are not relevant to our query. And to do that, you would be looking at like this kind of statistic like lower bounds, upper bound, and null value counts, specifically the lower bound and upper bound. So for example, if a query has a filter on like, let's say, value equal to 10, and if that particular value doesn't exist on that particular Parquet file, it won't even go to that level. So ultimately, the execution speed is a lot faster. And again, this may seem like a lot, but it's way faster in runtime. So it's just an abstraction of that. So I might just go and walk through a select query, like just select from this table where order is this. So it's basically this is the workflow. You go to the catalog, find the latest metadata file, go to the manifest list, manifest file, and the data file, and that's how it works. So the case study for the Netflix, right? So Netflix has a system called Atlas, which is basically a kind of time series metric system from their operational data. It has like in 1 month they had like 2.7 million files in close to 3,000 partitions. That's a huge amount of data for a month. And the problem was that they cannot process more than a few days of data. So like I said, the query is this one. Like it is a pretty simple query with just one particular metric and just a week of range of filter. And for this particular query with Hive, with Parquet, it took them like 9.6 minutes to just plan the query, not even execute the query. Now with Iceberg, with like partition data filtering, just partitioning and data filtering, it reduced the time drastically to like 10 seconds for planning versus 10 minutes like for planning, and overall execution time of like 13 minutes. And if you take a step further and use like Iceberg manifest, like with statistical information, you could also reduce it to like 42-second wall time. That's what they did actually, and this is directly from their slide, and that's what they achieved from this particular kind of like Iceberg and partition and min-max filtering. So that pretty much is about Iceberg. In terms of the top 5, I just thought it might be a good idea just to have an idea of what features like Iceberg enables, like things like SQL. Like I said, you can do run any kind of SQL using Spark, Trino, or any kind of engine that supports Iceberg. Things like hidden partitioning, like I was talking with Hive, you don't need to like maintain a separate column. Everything is automatically taken care of. And then ability to evolve schema is again, you don't need to rewrite an entire table for that. There are no side effects for that, costly rewrites. And then you can do things like time travel and data compaction easily as well. Just to give an idea of which engine supports Iceberg, this is a very comprehensive list today. Like every week, like every other time I hear like whether it's a big vendor data warehouse vendor like Snowflake or like BigQuery, they all support Iceberg now. And again, obviously like the data lake query engine like Spark, Trino and Dremio Flink, they also support it. Even Clickhouse, like now that we have a Clickhouse talk as well, Clickhouse also recently started a support for Iceberg. It's just read only as of now, but yeah, in the future it might be more of like the writes and stuff. So that could be something interesting as well. Yeah, that is pretty much it. I mostly work on the Iceberg, like the contribution from the open source perspective, code. Whether we also write a lot of like things around it. I'm working on the book, so feel free to reach out to me around that, and I'm also ready to take any questions that you might have. I'm sorry if I have like taken like extra. Yeah. Thank you.
Okay, so go ahead. We'll need a second to set up.
Sure.
So, yeah, go ahead.
All right. Does anyone have any questions, or like I can? Yeah. Or I can just Okay. Cool. I'll just get the mic to you. There we go. Thank you. Right. No. Yeah. So like I mentioned, like what Iceberg does, it basically makes and creates snapshots. So snapshot basically are a state of a table at a certain point of time, and you're historically keeping those snapshot. So Iceberg allows you to like store those snapshots, and basically you don't have to delete it unless you really want to like take care of those kind of storage and cost factor that are stored in that particular data lake. So those snapshot information are stored there. So you are able to query the data using a snapshot ID or just committed at timestamp. So you can use that. So irrespective of the operation, like whether it's like a smaller like insert or like some kind of upsert, you will be able to like keep that tracking in a snapshot. So every time you write something to Iceberg table, everything is a snapshot there. So ultimately you're collecting that historical information and you're keeping that linear history of like thing, and that's how you can time travel and go back and do analysis. Right, the Spark or any kind of engine, like So ultimately, like Iceberg is basically a format on top of like the file formats, and you have to use some kind of a compute engine like Spark or Trino to do that kind of things. All right. Anyone else? Okay, I'm gonna like pass it to you. Yeah, sure, yeah, and then I can talk to you in person. So yeah.
Yes, would you like to share about the data recovery and backup systems, all of that? I didn't.
Yeah. So this is not part of it, like but as long as because the storage would be like some kind of a data lake mostly. So then, it would be mostly on the side of the cloud vendor side. So if you're talking about those aspects, security and governance and controls on that, then it would be around that. But there are again lakehouse vendors like Databricks and us as well that make sure that you have a governance layer on top of that, and you can do things like replication and those kind of things like CDCs as well. So those are the kind of things that are taken care of. But in terms of security, if that was the question, that was mostly on the cloud vendor side. Recovery as well, yeah. Since you are storing all the data and you have all the major snapshots and all the major metadata and data stored in the particular data lake, those recovery aspects are you concerned about losing the data or something like that, or right? Yeah. So again, like those kind of failures and like failure side effect specifically comes from like compute engine side. So in this case, what Iceberg is basically doing is giving you the abstraction. So all those kind of like data that is storing is ultimately like being done by the compute engine. So that responsibility would be on the compute engine side, not from the Iceberg side. But what Iceberg is doing here is basically creating an abstraction on top of the actual data files that you have. Yeah, I can talk a bit more about it, and I'll just pass over the mic. There we go. All right. Oh yeah, I still have it.
Good.
Okay, test. Cool. Hey everyone, I'm Ankit. The title of my presentation is Postgres as a recommendation engine. It's not one of the common use case of Postgres, but here we are. A bit of word about my employer. Instacart is one of the leading grocery tech companies in North America. Almost 95% coverage in US and Canada, and some other stats you can look at. My team is product retrieval platform. So essentially, we own the infrastructure that powers all the search, recommendation, and all the app experience to get the products to the users. Well, Instacart is in the business of giving products to the users, so this is the core platform. The operations, uptime, reliability of all the 250 Postgres nodes that are behind this whole infra. Also, we own and build the read client and the write systems, so the ingestion system, we call it. So looking at the origins, how does recommendation engine in Postgres come from? So it's all started in 2012. So in PGCon, there was a hacking attempt that said finding similar. How do you find similar objects? This is the story of uncharted waters. After this attempt, we all forgot about it because the same year JSON launched in Postgres, and that all got the limelight. Well, similar. Okay. Yeah. So the core of the recommendation engine, certain recommendation engines, I should say, is embeddings. Embedding is nothing but a vector of floats and int, and it's a representation of any real-world object. The recent advances in OpenAI and all the generative AI is giving more limelight to embeddings. But embeddings could be of word, phrases, item, song, video, of anything. Sorry. A machine learning model converts object into the embeddings, and that's how we get them. On the inference side, problems can be converted into a similarity search problem in the embedding space. So when we want, hey Spotify, give me a song that is similar to this. So at the backend, Spotify is running the similarity search by embeddings. Now, embeddings are vectors that are close to each other in this hyperdimensional space. They are called similar to each other. So all what we need to do is find the similar objects by the distance. That's just a visual representation of what I just said. We had some words there. I don't see them. Bananas, avocado. A machine learning model takes them and converts them into vectors. Each word has its own vector. And then at the time of inference, we just take dot product or any other distance algorithm to say, hey, this is similar to that. Like apple is similar to red gala apple. They're almost the same thing. So I think I'm missing a slide. Sorry about that. So there and back again. So vectors are cool again in Postgres from 2012 to 2013. There's a blog post by Jonathan Katz from Amazon that who's published a State of the Union on vectors in Postgres of embeddings and workload containing machine learning inference. According to this, vectors have arrived, and although they're in early stages, it's like what JSON was in 2012, but it's new, cool, and shiny thing. Now, from that 2012 hacking attempt to 2023 of, well, vectors have arrived, somewhere in between Instacart took on an adventure. We built our entire search and recommendation infra on top of Postgres, scaled it to millions of users. So in one line, what's the search architecture for Instacart? Whenever a user issues search command, like you search for apples in your nearby stores, we convert that query into a Postgres query that uses a TS vector to perform keyword search, like old school search, not an embedding search. But we use an embedding personalized ranker to rank those results into what you like. So maybe if you prefer a specific brand of eggs, so they would show up at the top. Now, there is more to the story. We do embedding-based search as well for the retrieval, but that happens outside Postgres. Now that sends candidates back to Postgres for ranking. So in both of the searches, ranking is being done by Postgres, and one of the searches itself is being done by Postgres. And then both of the ranked set are combined in the application or in the backend to give a final result set to the users. Now this is fairly inefficient, as everyone can see. With the new advances in Postgres, we are exploring to combine everything into a single query, both kind of the retrievals and then the final combination. That's still an experimental stage, I must say. It would take a few months for us to sort of see if that works or if that sees the light of the day. But even the Postgres full text search, the old school search, is sufficiently fully featured. For us, it supports filtering on geographies, like we don't show stores of San Francisco to us to here. Latest availability information, whatever we have, if a product is not available in the store, that information is conveyed to the search system, and we join the data in the Postgres. And a bunch of other features like cover density algorithm, CTR boosting, in-house QE boosting. So I don't know these words. I've been given these words by our search team telling me that Postgres search is awesome. We like it. And then the final set is ranked by a dot product of users, embeddings, and product embeddings, the standard personalization ranker. This is sort of a diagram of whatever I said. The key thing is that client can choose to re-rank the items another time. It's called a second class ranker. All this is first class ranker, according to some information. For example, if you search for ground meat, and we know that in the past you usually order Beyond Meat, there is some sort of opportunity for re-ranking whatever is returned by the Postgres. So let's talk about this Postgres cluster. What exactly is this product retrieval cluster? So this cluster is designed to be a write-ahead cache. There's nothing like write-ahead cache in computer science, so I just created that name. It's essentially a reverse write-back cache. So there is a write-back cache, and sort of we put the concept on the opposite. So it's reverse write-back cache. The clients or the users, the backend systems, only have read-only access. They can retrieve the products as the name. They cannot write. So we completely own the writes. They're written by whatever inserts and updates go into the cluster by specific workers, background jobs, pipelining the row upserts from whatever the source of truth. So it's a cache, it's not a source of truth. We don't guarantee atomicity or transactional consistency, neither it's needed. Even our replicas are staggered, like some replicas would have no replica lag, some we force it to have 5 minutes, some 15 minutes. So there's a staggering replica lag on different replicas. We use NVMEs, fast disks, and we aim for a high shared buffer usage, which means most of the queries would not even hit the disk. They just get their data from memory. And bots help us do that, actually. So when we get hit by a lot of bots, it helps us keep the data in memory. We've seen latency go down when we get hit by a lot of bots. One of the key features is that replica is never promoted. If a primary dies, it dies. We simply replace it up, and the replica can continue serving stale data while primary is being rebuilt. We aim for an hour, 1 hour of primary downtime. We just stop our workers writing into the primaries. It allows us to sleep at night. We don't get woken up by primary loss. So this is sort of the topology diagram of the whole system. The app container can be misleading. Think of it as backend container, not the app. It talks to a pgcat pool. Pgcat is nothing but a proxy. We know the pg bouncer or pg pool if you've heard of it. It's a new proxy, and that fronts all of our replicas. And on the right side, we have a big ingestion state machine. I won't go deep into that, but essentially its job is to write CSVs into the primary. The primary then ships logs to the replica. We don't do streaming replication as well. We just ship logs to S3, and the replicas pull whatever they need on their side. At the center of this is a tool called PG Backrest. That is very reliable. In the last 3 years, I do not remember getting woken up or getting paged for any replication problems or any backup problems. It does both. So it serves our backups, full and incremental both, as well as it communicates the wall to the replicas. Wall is nothing but the write-ahead log that Postgres communicates to its replicas. If you're curious about PGCat, what it offers is some sort of a sharding capabilities. Earlier, the backend containers, they used to have connections to all the shards. Let's say there's 50 shards in a cluster. A container would have Postgres connection to all the shards. PG Bouncer doesn't support that. PGCat, what it does is it allows us to have single connection from app to PGCat, and PGCat then chooses which shard to send the query to. And eventual goal is to move more client-side burden of sharding and banning. Banning is like if one of the replicas here goes down, the hardware fails, clients right now ban that replica, that, hey, this replica has X amount of queries failed, there must be wrong with it, something. Right now, all that logic is written in the backend itself. With flexibility of PGCat, we intend to move some of that banning logic as well into the PGCat pools. Last thing about this slide is that PG Backrest is being mentioned just in passing, as if it's just a small thing. But it's one of the most reliable pieces of software I've ever seen. It does a lot. It does a lot of throughput, and it just sits there and does like workhorse. Example of what's the staggered replica lag. These are different replicas, and you can see what sort of replica lags do they have. 0, 5, 10, 15. Why do we have staggered replica lags? That doesn't seem ideal, and you're not serving consistency. Yes, that's a valid question. So what we saw is whenever we run a migration, that's a DDL, like add a column, remove a column, Postgres would take table exclusive logs, and if the migration is bad, it takes a long time. It takes a few minutes. We don't want all the reads would be stopped for that 1 or 2 minutes. Also, certain vacuum processes in Postgres on PG catalog tables, especially, they have very strong hard locks that the whole database freezes for whatever time that thing is being vacuumed. So previously, the whole site would be hard down. Now it's only 1/3 down because most of these lock the last 1 or 2 minutes, and if we have staggered 5 minutes, we only have 1/3 of the site down. And if clients have a good retry mechanism, it's essentially a degradation and not a complete shutdown of the whole system. That's the Postgres setting that we use to enforce lag. Now, another interesting thing happened is, so we see this lag. In some of these situations when there is already existing lag, a new transaction coming is not applied lag, because Postgres thinks you're already, let's say this was already 15 minutes lag here because of some other natural situation. Postgres doesn't apply any lag. So in situations when we are not sending any writes, think of the situation where primary doesn't generate any write, it's just sitting empty. Replica thinks it is lagging for that time. Last 5 minutes, I haven't seen anything, it must be a problem with me. Now, next transaction comes, let's say, with a lock. Lock gets applied immediately. And then there is a transaction comes in, Replica is aware of its situation, that it's not lagging, and then the lock gets unlocked. So the unlocking happens after 15 minutes. So the lock, which was supposed to be microsecond, is now as long as 15 minutes. That's a very quirky edge case we saw with this architecture. And the way we have solved is we never allow Postgres to be not sending anything. So we have a dummy write that keeps saying, just insert any random row in one of the tables that we don't care about. So we never see this situation. So going back a bit of a eagle's viewpoint, what happens in the whole picture outside Postgres? Of course, machine learning training, we don't do that. All the tuning, hyperparameter of ML models, generation of embeddings, that doesn't happen in Postgres. Combining embedding-based retrieved candidates and keyword-based, because only one of these things happen in Postgres, we can't combine that. And some sort of a query understanding step before formulating a PostgreSQL. For example, milk chocolate and chocolate milk are entirely two different things for our users, and we want to understand the nuance and then formulate the SQL query. So all that happens before outside the Postgres. What happens within the Postgres? The indexing or injection of trained model of the embeddings is via merge-like command. Merge is a new facility in Postgres where you can bulk upload data. We are still on the old version, so we have a merge-like thing doing this job. TS vector-based keyword search. And after the search, a dot product custom written extension, we wrote the extension ourselves 3 years ago, that multiplies users in product embeddings and ranks all the retrieved products. Then we do joins for inventory availability, CTRs. CTRs is click-through rate. Like if some products are more bought, we want to boost them up in the ranking, and bunch of other ML-generated scorings. Now, the key with CTR is that we have seen some failures as well. Like we were doing some campaign with Red Bull, and people, whenever they search Red Bull, they were being shown red bell peppers because red bell peppers have really good CTRs. But the other ML model generated scorings are sort of balancing it out, like understanding that the query intent is narrow or wide. We want to use CDRs only in the wide intent, like if you search for fruit, we use CDRs. If you search for dragon fruit, it's a very narrow intent. We don't want to use CDRs. So all those things happen inside the Postgres. So one sort of a distinction between KNN and ANN. What we use is KNN, which is absolute distances between two embeddings. That doesn't scale well. The way we are using is we just apply KNN to maximum of 500 products after search is already done. If we were doing full search, which is search through millions of products and then give 500 to the users, we would need some sort of approximate algorithms. So ANN's latency, or the time taken by ANN, they don't grow as to the square of the number like the KNN would do. Yeah, so I mean, to move forward in this sort of a world, we would need to start adopting ANN. The modern version of Postgres have extensions to do that. Like PG Vector, Postgres ML, there are a bunch of those that can be used. So we are exploring the use of that and using ANN to be more fast. The KNN extension that I said that we have, that's all it is. It's 20-line extension. It does multiply 2 vectors, returns the sum. There's not much magic to it. It's written in C. It's supposed to be fast. It does its job well. So that's our ranker. The good thing is the same dot product can also give us cosine similarity, which can be useful in some situations. Cosine similarity is nothing but your absolute dot product, the dot product divided by absolute values of the vectors. So just angle of the distance. So what have we gained by this sort of big experimental project? The first is model update speed. How fast a new ML model can be updated and served in front of the customers has been one of the key features of this. How fast an ML engineers can iterate, experiment, and improve their work is, I guess, one of the key metrics for any inference system. The second is developer velocity, development velocity. We use Postgres, Rails, Active Record, the standard things which a usual product engineer uses, and they don't have to change anything compared to their transactional systems. The biggest win in terms of the user experience is that you don't see empty carousels. Previously, what used to happen is that search system would give 20 products to the front-end app, and app would combine that with availability, and most of the 20 products have been sold out. None of them are available. So the app would make another call to the system, another call. By the time user says that the app is not even opening. So we have combined all the traditional fetching, filtering, joining, and search into a single system. There is no more back and forth. There is no more data sloshing around into multiple systems. Users get their data in their first call. This has moved, I would say, significant business benefits for our company as well. Do you know Postgres flexible data models? We've also been able to include multiple flavors of CTRs that have enriched the relevance of the ranking. Yeah, the last is availability machine. Now, with this approach, the availability machine can be more complex, much more enriched, and it can have much more interesting machine learning models giving us information that is this item available or not. What we've seen in the last few years is that the system has operated very reliably with 5 nines, much faster, more throughput in the data pipeline for retailer information. Not just retailer information, but all the machine learning model that go to the users. They are much more faster now. Much better P99 latency. That's for the users. Our previous system, because of that empty carousel thing, multiple different data systems were called. We have much better P99. I would say it's more like 10 times better P99. I'm going to skip that in the interest of time. This is some details about the ingestion. Maybe we can just look at the numbers. Just the total number of writes going to the system is 15 billion per day. To give you the scale, the number of read queries is still 6 billion. So we do more writes than reads. How do we ingest that many records a day in this cluster? Well, we shard the data, so there is not a single primary. And also we use copy plus on conflict bulk upsert. So we copy the whole S3 file into the Postgres and then on conflict bulk updates. This is sort of a two-step process, but it sort of allows more throughput. And who sends most data? Is the retailer data or machine learning? Well, that's one of the not very surprising, but a bit surprising. Most of the writes are the updates to the machine learning models. Now, the argument of vector math and complex compute workloads, maybe for ML or some other project, in last few months have become more acceptable in people's mind that yes, Postgres can do this, and that's essentially aided by PG Vector and all the cloud vendors that have adopted PG Vector. But in our initial days, we used to get very strong opinions. I don't think you're doing the right thing. That's very odd what you're doing. However, looking at Michael Stonebreaker, who proposed the initial Postgres, his original 1986 paper, it had explicit 2 goals. One of them, first goal is store complex objects, compare complex objects. being able to support complex objects. The second goal was make it more flexible. People can write their own extensions and create more complex objects themselves without involving the Postgres team. So essentially, there is nothing new under the sun. This has happened before with JSON and other things. It's going to happen again. We have seen the same story play out before. In the words of Andy Pavlov, he says, "What goes around comes around and around and around." The puzzle pieces fit nicely together. Machine learning and the new vector math support in Postgres is not surprising. I would say Instacart just happens to be one of the early adopters of this approach. That's all. Thank you. Any questions?
Questions?
That was a brilliant talk. I have a question about Instacart's plans for PG Vector and Postgres for the next 5 years or 10 years. Is Instacart all on Postgres, or are you building a layer internally that can abstract over multiple databases like Chroma or other vector databases that last year?
At this point, we are exploring all options. Right now, we do not use a vector database. Even for embedding, we will use a specific service. PG Vector remains a primary contender just because there's a lot of other things which we can do inside the Postgres. But the evaluation we're
Which means sadly we are out of time. So what we're going to do is we're going to do the networking down by the elephants outside. Does that sound good? Can everybody grab some pizza on your way? I just want to say once again, thank you so much for the speakers. We would love to know how this event was. If you don't mind snapping a QR code and letting us know about that. We'd love you to join us for the next one. I'm assuming everybody in here found out about this through meetup.com, but in case you're not in our Toronto OSDI meetup group, we would love to